So let's take a look at chapter 15. Yeah, let me take a quick peek at this and be sure. Yeah, I'm still there. Okay. So now we're getting into This is not spectroscopy. This is spectrometry. Okay, there's a difference. Spectra means series of data points or series of measurements, and they occur regularly based upon some other factor. Now, when it's spectrometry, spectroscopy, it's based upon scope, which is eyes, right? What you can see, visual, light. Spectrometry is based upon measurement, metric measurement. So we're measuring different masses of fragmentation products. Let's go in and look at it now. Oh, I better change some. Second. Let's change this one here. This is 15. And it's titled Structure Determination 1, Mass Spectroscopy. It's a big title. Structure 1, Mass Spec. So if somebody says mass spec, that's what they mean, mass spectrometry. Okay, so a little background. When organic chemistry was relatively immature, actually, when I was taking organic in college, my first round with it, this is the way that we were told that structures were determined for products and for intermediates. Is chemists would get the molecular structure by measuring a compound's physical properties first. Like you would have density, melting point, freezing point, boiling point, whatever the case may be. You would get reactivity with certain compounds. And you have a standard set of compounds, and how reactive is it with this. And then you would carry out reactions that were designed to provide information about the presence or relative position of specific functional groups. In other words, you tried to reconstruct the molecule with known synthetic steps. And if you went through these synthetic steps and you knew how they reacted every time, and you ended up with the same molecule that you isolated from a different procedure, then you were pretty sure that you had an idea of what its structure was, right? Very, very tedious, time-consuming, and fraught with mistakes. Right. Today, with the advent of spectrometry and spectroscopy, we're able to determine the structure of a molecule with these various featured instrumental outputs. Right. And the first one we're going to look at is mass spectrometry. Later we'll get to in chapter 16 we'll get to infrared spectrometry. Remember that the electromagnetic spectrum has the lower energy, longer wavelengths would be infrared. Be visible would be red, then we get infrared, and then you go to microwaves, then the radio waves. You don't get much information about the molecules beyond infrared. So we'll go back the other way. On the other side of the visible is ultraviolet. Ultraviolet gives us some information about the structure also. And we're going to cover infrared and ultraviolet in chapter 16. UV and visible, actually, both of them. And then 17, we're going to look at nuclear magnetic resonance. And nuclear magnetic resonance, the ultraviolet and visible spectra, ultraviolet, visible, and infrared, are based upon electrons or ultraviolet and visible electron movements, and infrared is based upon changes in bond conformation, like stretches and spins and that type of thing. And then nuclear magnetic resonance, though, that goes down into the nucleus itself. So if you've ever had an MRI, yeah, that's what they were doing. They were looking at the nuclei, usually of the hydrogens in your body. And let's see, they would have to be, might have to do it on deuterium. I don't know. We'll take a closer look at it when we get to chapter 17. Okay, this is just an overview, and we pick out some high points, some salient points from representative mass spectra. Also, these spectroscopic techniques can be hybridized into other analytical techniques. When I was working for the government, in our lab, we had a gas chromatograph that was coupled with a mass spectrometer. So the output from the gas chromatograph, so we separate the compounds in the gas phase, and then we send those fractions into the mass spectrometer, and it does its magic and produces what I'm going to show you in a minute. And with that information and a library of spectra from known molecules, you can get pretty close to what the compound is that came off that fraction and its structure. So they call it GCMS, gas chromatograph mass spectrometer. Okay. This particular diagram or picture of a mass spectrometer, this is a magnetic sector mass spectrometer. In other words, the separation of the different masses of fragments based upon their behavior in a magnetic field. These are very accurate, and sometimes we put them in tandem. We'll have a magnetic sector mass spectrometer, and then the output from that goes sequentially into another mass spec and give you finer resolution. They're very expensive. But we also have other ways that are cheaper to separate the masses. One of the more common ones is called the quadrupole, and that's the one that was used in my mass spec. I don't think we could have afforded a magnetic sector. Anyway, so what are the steps? Right, you have a sample, and I think we have black and white on the next slide. But while we're looking at the picture, I think it'll be easier to understand. We have a sample that doesn't have to be a very large sample, be very small, like a microliter would be enough. And then the first thing you do to the sample, if it's liquid especially, is you vaporize it. It has to be in the gas phase. So that's number 2. You vaporize the sample, and then you you send it into this region where we have an electron source, electron beam source that's bombarding your sample as it enters that chamber. And what those electrons do is they interact with the electrons of the molecule, and they knock electrons off. If you adjust it right, you can knock one electron off. So that'll give you ions of just one positive charge. And once you've got a charge, you can accelerate that ion between the positive and negative plates. Right? So you can get it up to speed. It has to be moving. And then the other thing that that electron beam does is if you have any weak points in your molecule, those electrons will come in and break it. They'll break the bonds and form separate ions. Some of them, they don't form ions, and some they do. But it's different for each molecule. And once you form the ions and you get lots of different fragmentation parts that are ionized, then you can accelerate them through that electrical field and into the magnetic sector. So when they go into that magnetic sector, say the magnet is like this, magnetic field's this way, then as the ion goes into that magnetic sector, it will bend under the influence of the magnetic field. Okay. Now, if you have two ions with the same charge, they will experience the same force, the magnetic force that's bending them. If it's the same force, but they're different masses, then the lighter one's going to come over here and the heavier one's going to come over there. That's how you separate them. And then your detector, and the detectors we have now are so fast, they can count individual ions and tally them up. And then they give you this report. The mass spec report will have relative abundance. You could say fractional abundance or percentage abundance, it doesn't matter. I think in this set of slides, we're using percent. And you get these peaks. And the bigger the peak, the more abundant that ion relative to the one that is the most abundant. We call it 100%. So let's go to the next slide. Let's see. Here we go. So here's the vaporization phase. All right, you got to have it in a gas phase. So if it goes in as a gas, like from my gas chromatograph, then a no-brainer. It's already a gas. And then once vaporized, it starts to drift through that region, and then you hit it with fast-moving electrons. Right? And that electron beam forms the ions. It also gives you fragmentations. And so you get the fragmentation parts. Some of them are charged and some of them aren't. So this is known as electron impact ionization. There are other ways to ionize your samples, and they're specific on what types of ions you want from your samples, what type of sample is going in, and whether or not you want to treat it more mildly than an electron beam. You can do chemical ionization also. But for our example here, this is electron impact ionization. It gives you a fragmentation pattern. Right? So we report these as mass to charge ratio. And if our spectrometer is adjusted in such a way that we're pretty sure we've got only +1 charges, that's it, then you divide everything by +1 to give you a mass to charge ratio. And that means that their relative positions are based upon mass only. Right? So the further out you are, that mass ratio to the right, the larger the mass. So when we say mass charge ratio, if the mass charge ratio is 87, then we're pretty sure that it's 87 units for that molecule, for that fragment. And the relative abundance is based upon the highest peak. And that piece is known as the base peak. So in this example here, our base peak is at 57 mass charge ratio. And we just adjust the whole thing to 100% for that base peak. The tallest peak is there. So it's everything else is relative to that. The largest peak let me see. The M+ peak is taken to be the compound's molecular mass. So that would be the complete molecule. Here, we're actually giving you a pattern for our known molecule, like 1, 2, 3, 4, 5, 6. So that's hexane. This is the mass spec pattern for hexane. It gives us large abundance for fragments that are 29 and 43 and 57. And then the largest one out here. Now there's a little tiny one down here, and we're going to talk about that in a minute. But the largest peak out here at the far right is taken to be the mass of hexane. So hexane is C6H14. Right? So let's just rough it out. There's 14 for hydrogens, and 6 times 12 is 72, right?
6 times 12, you said?
Yeah, 6 times 12 is 72, I think.
Yes.
Okay, so 72 and 14 would be 86. So there it is, 86 units. And that's the compound's molecular mass. All right, we're going to introduce this, what's called the nitrogen rule. A compound containing an odd number of nitrogen atoms typically has an odd molecular mass. And a compound containing an even number of nitrogen atoms or no nitrogen atoms typically has an even molecular mass. So what was our previous one? 86 is even. Well, there are no nitrogens there. So that nitrogen rule holds for that situation. Okay, so there's our large fragment, 86 for hexane. And these are the possible fragmentation patterns. If you fragment between the number 1 and number 2 carbon, then you get a methyl radical, methyl free radical. Notice it's only got 1 electron. So what's happened there is we've broken the bond, and 1 electron went H3. Yeah, H3. This fast-moving electron came in here and broke that bond and went like this. Right? 1 electron went that way, and 1 electron went this way. That's called homolysis. No, same. Heterolysis. Hetero means other. So this one went that way, and this one went to the other. So that's what you get. You get a 5 carbon fragment with that first option. With the second option, you get a 4 carbon fragment, and with a middle breakage, you get a 3 carbon fragment. Okay, and that each one would be from top to bottom 71, 57, and 43. So let's go back. There's 71 right there, 57 and 43, right? Yeah. So those are there in the mass spec that the graph that we see. Now, what about this one? This is
I'm confused why they're calling it ethylbenzene.
ethylbenzene. Yes,
Why isn't it just benzene?
because it has an ethyl group on it. Right? See that kink off to the right?
Yeah.
That's an ethyl group.
But I thought the benzene had that little tail where phenol.
Oh, if we do something like this, and we're talking about functional groups, right? That would be phenol.
Yeah.
This would be benzyl. And this is the one we have there. So it's either, if we use this as our root, then that would be ethyl benzene.
Okay, I get it now. I was getting confused. I was thinking that was the benzyl, and then you take off the one.
No.
Yeah.
I guess you could call it, if you had this one, call it ethane here. Ethane. This would be phenyl. Phenylethane. It would also be a name. But we use this as the root, but typically you use that as the root. Unless it's in that the priorities, functional group priorities.
Yeah.
Should have that available for you. Okay, so if this is the spectrum for that one, then the farthest one to the right with the big peak, this one way out here, which will be, let's see, 5, 10, 15, 20. This is 5, 6, 106, I think. 106 atomic units. Let's see what the let's see. Let's take this molecule and do that, do that. This is a CH3, this is a CH2, and this is a 1, 1, 1, 1, 1 there, like that. So we got 1, 2, 3, 4, 5, 6, 7, 8 carbons. And we have how many hydrogens? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. H10. So that would be 8 times 12 is 96.
Yeah.
Okay. And this would be 10. So those two together would be 106. Right, so that's it. That 106 on the far right, that's our what did they call that? The name. That's our, they don't give it a special name. It's the molecular mass. That's the molecular peak. Okay. And then the this 100 right here, the reference base peak is at, let's see, 80, 85, 90, 90, 91 is at 91.
Yeah. Or 92, something like that.
So let's say, let's just assume it's that one. That would be 5, 15. So we lost 15. How do you lose 15? Well, you lose a 12 plus 3. So that would be there. Right. So the base peak was probably this ion right here. And that fragment was not picked up because it's not charged. Okay, what was the question? Identify the M plus peak. Okay, we got that one. What is the formula of the ion responsible for the base peak? Oh, we did it.
Yeah.
I didn't even read the question.
And it was all right too.
Huh?
You got it all right.
Yeah. Oh, amazing. Okay. Let's see. Oh, now we're going to talk about that little peak to the right of the molecular peak. Right, you see a tiny peak just to the right. Right, what is that? Well, that one is close enough, I think, to be an M plus 1 peak. In other words, it's at 87 rather than 86. So an M plus 1 peak can be explained as a contribution from an isotope. Right? So if we have 86 as our race, we have 86 as the molecular peak, then you might have a chance where that's with carbon 12. But if you have carbon 13, that gives you another nucleon, which adds to that, making it 87. So that's known as the M plus 1 peak. And it only happens in molecules where the abundance of the isotope is high enough to influence the overall. And I think that's on the next slide. So with carbon, carbon-12 is almost 99% of the abundance, but carbon-13 is a stable isotope. It's not radioactive, and it's about 1%. Right? So there's enough of it there that we can influence that. We can give it the N+1 peak, and it's detectable. Now, if we tried to do that with hydrogen, it wouldn't work. Right? Deuterium is too small. Nitrogen is almost there. You might get a little nitrogen peak, but oxygen is too small. Chlorine is a huge abundance for its next isotope. So chlorine, the dominant chlorine isotope is 35 mass units. And the next abundant one is 37. So this is going to produce a peak to the right. That's an M+2 peak, right? Because we've gone from 35 to 37. That's where we're headed. And there, all those calculations at the bottom are to confirm just what I said in passing. All right. So for small and medium-sized molecules, M and M+1 peaks are often identified as two peaks with the highest mass farthest to the right in the spectrum. Right? And there's going to be a ratio between the two. The difference is 1 mass unit. So if the for the M+2 peak, this is more than likely a well, let's see. Hold on a second. Let me back up. Did they put bromine? Yeah, they did put bromine in there. Okay, so bromine goes from 79 to 81. Right? Bromine, 79 is the most abundant, but this is fairly abundant. 81. So there's a two difference there. Two difference here, two difference here. So you can get an M+2 for both chlorine and bromine. You can get one for sulfur too. Look at that. 4.21 for 34 sulfur versus 32 sulfur. All right. So you can get an M+2 for sulfur. You can get an M+2 for silicon also, if it's part of the molecule. All right. So the M+2 peaks. What we see is that with M+2 peaks, differentiating between the chlorine and the bromine in a molecule. If you have an M+2 peak there, this one also has an M+1. See? But then we go out another step and we get to M+2. If the ratio between the molecular peak and the M+2 peak is about 3 to 1, then that peak represents a chlorine in the molecule. If it's a 1 to 1 ratio, then we're looking at bromine. That's how you tell them apart. All right, so here's an example of a bromobenzene. With an M+2 peak. Looks like it's got an M+3 also. All right. So, so 1-bromo 4,1-methylethyl benzene will give us this pattern. And what we're pointing out here is smaller fragments containing bromine also. Right? It doesn't have to just be the whole molecule with the bromine on it. We get fragments with bromine on there too. And we see these fragments have twin peaks that are the same size. So the pattern holds for smaller fragments also. Twin peaks. Wasn't that a soap opera?
I don't think so.
No. Was it a movie?
Maybe it sounds familiar, but
Yeah. All right. Next. Okay, does the compound that produced the spectrum show here contain chlorine or bromine? Well, let's see. Our largest peak, we got a peak out there that's 114, and then we got a 115 outside of it. Now, is that a 3-to-1 ratio? No, it doesn't look like it's 3-to-1. Let me see what Cardi has to say. Where are the M plus and the M plus 2 peaks in the spectrum? Right? At the high mass end, there are substantial peaks at 112, 114. 112 and 114. So there's 112. So 112 versus 114 is right. And the ratio between 112 and 114 heights is about 3-to-1. So that's chlorine. And then 113 to 115 is another fragment where you've got 2 steps. And 113 to 115 is also about a 3-to-1 ratio. So we're looking at chlorine. It was jumbled. So it was hard to tell which one was which. So I think what we're looking for is 2 steps, right? So 2 steps from 12 is 14. Their ratio is 3-to-1. 2 steps from 13 to 15 their ratio is also 3-to-1. So we're looking at chlorine. All right. Estimating the number of carbons from the M plus 1 peak. Starting to get sticky. The ratio of M plus 1 peak intensity to the molecular peak increases as the number of carbon atoms in the molecule increases. Well, that makes sense. If you increase the number of carbon atoms in your molecule, you increase the chances of introducing a carbon-13, right? So the relative abundance of the M plus 1 peak should increase. All right, so here we have 1, 2, 3, 4, 5, 6. There's the hexane, and this one is 2, 4, 6, 8, 10, 12. This is see, decane. I forgot what happens when you go past 10. To name the compound. All right, so we're looking at, we found the base peak, and we also found the molecular peak, and then the M plus 1 peaks. Okay. Well, that doesn't tell me anything. Right? The peak intensity increases as the number of carbon atoms in the molecule increases. Well, it's all relative to the base peak. That's why we can't compare the two, right? Because the base peak is normalized to 100%. Yeah, that's the problem. We need absolute intensities in order to do that. So here's a useful formula. The ratio of M plus 1 peak to M peak intensity increases as the number of carbon atoms molecule increases. The number of carbon atoms can be estimated if you know the intensity of the M plus 1, ratio it to the intensity of the M plus. Okay, so in that case, we're good. We don't have to compare apples and oranges. You take the 2 intensities, and you take the M plus 1, so over the M, and that's usually going to be a fraction. Right? The M plus 1 is going to be a smaller number. So you're going to get a number less than 1. And then you multiply it by the ratio of 100 to 1.1, which is about, what, 90 something? And that should estimate the number of carbon atoms. Now, it's not definitive. I mean, it's not accurate. This is semi-quantitative at best. How about this one? All right. Well, it looks like the base peak is our M peak. or molecular peak. And then the one right next to it is what? That's about 7 or 8 divided by 100 would be that first ratio. What do they call it? They're calling it 7. So 7 divided by 100 times 100 divided by 1.1 is 6.4. So we have roughly 6 carbons in this molecule. Let's see. They didn't tell us what it was. Okay. So determining the molecular formula from the mass spectrum of an organic compound. Well, definitely you want to assign the M plus peak because that's going to give you the molar mass. And then if it has an M plus 2 peak, it's probably got a halogen in it. And then the ratio of those intensities will tell you whether it's chlorine or bromine. And then you calculate the number of carbons based upon that, the ratio of the M and the M plus 1 peak. Oh, I got ahead of myself. Then you can see if you've got a bromine or a chlorine in there. Subtract the masses. Once you know how many carbons there are, then you can subtract the mass of the carbon atoms from the value determined in step 2, which is the mass of the molecule. And to see if there are any heteroatoms in there. And then you see if your hydrogens can account for the rest of the mass. Once you've determined whether there's bromine or chlorine in there, and you've subtracted the number of carbons from the total mass, then you see what's left over. So you have a complete molecular formula that could be feasible. If the number of hydrogen atoms is unreasonably high, then consider adding another non-hydrogen atom like carbon, oxygen, fluorine. So it's more of a detective story. It's not definitive, but well, that's my opinion of organic chemists. I mean, they're glorified cooks. So here's an unknown. We're going to go through this one step by step. We're not given the M plus peak, but notice that the 2 highest masses are 129 and 130. And so that means probably the 130 is an M plus 1, and 129 is our molar mass. Then we assign, yes, I already said that. So our unknown is 129 units. Plugging the intensities of the M and the M plus 1 into our equation, they have to tell us what that is. 2.4% abundance versus 30% abundance. Okay, then take that ratio, and we have maybe 7 carbons in this molecule. Then the nitrogen rule suggests that the molecule has an odd number of nitrogen atoms. Okay, that nitrogen rule said what? The value 129. 129 is an odd number, so we should have an odd number of nitrogens in there. Step 3B can be skipped because the spectrum does not contain an M plus 2 peak. So we know we don't have any halogens in there. Then we subtract the mass of those 7 carbons from the value. They weigh 84 units, and was subtracted from 129 leaves us 45 units that must be accounted for by non-carbon atoms. All right. An odd number of nitrogens. Since the nitrogen rule suggests there's an odd number of nitrogens, how many are there? Well, we probably have to guess. Right? If there are 3 nitrogens, that's 42. Right? So 42 from 45 leaves us with 3 units that could be accounted for by hydrogens. However, it's unlikely that a compound containing 7 carbons and 3 nitrogens would have just 3 hydrogens. So we back it down, right? Instead of three nitrogen atoms, we go to odd numbers, right? So we go down to one, right? Contain just one nitrogen. That leaves a mass of 31 units to account for. Okay. The remaining 31 units cannot come only from hydrogen because there's just not enough of them. We can't have 31 hydrogen atoms in that molecule with only 7 carbons. So we probably have another molecule in there, a heteroatom, either oxygen or fluorine. So if we write out our formula with 7 carbons as our beginning, and then we have hydrogen with an unknown number. But if we have a nitrogen, we have one nitrogen, and then we make up the difference with an oxygen, that means there's only room for 15 hydrogens left over. But if we fill in, rather than oxygen, we put a fluorine in there, which is heavier, then we've only got room for 12 hydrogens. So these are 2 proposed formulas, right? C7H15NO or C7H12NF are possibilities. Unknown 2 has a mass spectrum shown here. All right, so we have a high peak of 152, and we also have a 150. So a 150 to a 152 is 2 units difference. What that means is that it's probably bromine. We've got bromine in there. And then if we take the M peak, which would be on the left, right? We've already got the M plus 2, so the one to the left is going to be the M, right? That's 150, and its relative abundance is 14.7 and 0.7 for the small peak. And we do that ratio formula, and that gives us about 4 carbons. Okay. Well, the mass is 150. Out of 4 carbons, and we've determined that our M plus 2 is bromine. So, excuse me, 4 carbons. 1 bromine is 79 units. 4 carbons is 48. So if we only have 1 bromine and 4 carbons, that leaves us 23 units left over. Nitrogens cannot account for the remaining mass because the mass of the lowest even-numbered nitrogen atom would be 2. That would be 28, so that's too much. So we don't have a nitrogen in there. Right, did that one fly by you too fast? The nitrogen rule says that if it's an even number, then we have an even number of nitrogens. Right? An even number of nitrogens would give us 28 units, and we've only got 23 left over. So there's no nitrogen there. So can we make up the difference if we can't accommodate 23 hydrogens? Right? Therefore, we need another atom, either an oxygen or a fluorine. So that's our proposed model. Right? If we use up some, we use up a 16 with oxygen, then we only have enough for 7 hydrogens. If we use up, let's see, fluorine is 18. We use up 18, now we only have 4 hydrogens. Okay. Fragmentation pathways in mass spectrometry. You can get a whole lots of different fragments from chemical process. Okay, yeah. When we fragment the molecule, you get lots of different patterns. And we looked at different ways to fragment a molecule. So we're not going to go through those again. Alkanes, how do they tend to fragment? Well, the parent molecule, of course, is just going to lose 1 electron and make it a positive. And then we could, that first example on fragmentation of hexane, if we fragment between the 2 and the 3 carbon, we get a 4 carbon, a butyl cation. If we fragment the methyl group off, we get a pentyl radical. The tendency there, so what we're looking at is we've got to produce an ion in order to go through the mass spec. And we're only going to get one ion out of a fragmentation. So in the top one, the butyl positive ion is more stable than the pentyl. So in the second fragmentation, where we chop off a methyl group, it's going to carry the positive charge. And for this example, where we have 2-methylpentane, we have a tertiary carbon. And if we fragment that one, that's ideally where the fragmentation is going to occur, simply because if we produce the carbocation from that one, then it's going to be more stable on that secondary carbon than it would be on a primary carbon. So the propyl radical is thrown away, and we keep the isopropyl cation. Let's see, how about 2,2-dimethylbutane? With additional branching, fragmentation gives rise to fragment ions with relatively high stabilities. All right. If a fragment ion is sufficiently stable, then the M+ peak can essentially disappear entirely from a compound's mass spectrum. That means what that's saying is, if the fragmentation patterns give us very, very stable ions, then we'll fragment the whole molecule rather than leave anything behind for the M+ ion. So it may disappear. Let's see. Alkenes and aromatic compounds, loss of an electron from the pi bond. Okay. So rather than fragment it, alkenes would tend to produce a lot of molecular ions because they're still stable. They give up a pi electron in order to form the positive ion, and you don't have to break any bonds. I mean, you don't have to break any sigma bonds. So that's why the peak over here, this 84 peak, is so huge. And the other thing that I didn't discuss was resonance stabilization. Right, you can still get breakage in there, as evidenced by the patterns over here. You still get these fragment peaks, but your molecular peak is very large. So when you break a bond in an alkene, you're looking for resonance stabilization. Right? So if you've already formed the ion and you get hit with another electron, it may break off an ethyl group. And when it does that, what does it do? Breaks off an ethyl group. We've got to, I'm not following this. They're starting from the carbocation and then 2-butynyl cation. So we're breaking off an ethyl group and leaving us with 4 carbons. Oh, I see. I see. When I missed that arrow. No, that's the wrong arrow. That's the resonance arrow down at the bottom. I want to see this. What was that? 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. And we formed carbocation here. And if we're going to break it here, which way do the electrons go? Well, it says we're forming an ethyl radical. So that means the electron has to go this way. Right? So if the other electron goes this way, no, that wouldn't be right. I don't get it. It says we're forming a double bond here. So that means we have to get both electrons go that way. No, goes the other way. Yeah, it has to go this way. So both of these electrons go 1, 2, 3, 4, go here, right? And form that double bond. Yeah. Did I confuse you yet?
I think I'm keeping up, but I don't really know either. I think I am.
I'm just trying to follow what they're saying here. And once you form this bentonil cation, then it can resonate and move the positive charge around. All right, so what effect does that have on the fragmentation pattern? Well, it's not telling us, right? So if they don't care, I don't care. Because I haven't thrown out any slides. Okay. How many slides we got in this set?
We have 57 and we're at 45, so
Oh, okay. So
yeah, we're good.
we're going to finish all right. So resonance stabilized fragment ions, formation of benzyl cations. So in order to be a benzyl cation, that molecule would have to be broken to leave one methyl carbon attached to the phenyl ring. And that means it would break off a propyl group, wouldn't it? Oh, they're going to show us. Good. Okay, so you know what they're saying here is that we're forming a relatively stable carbocation in the first electron strike. And then after that, it's going to get hit again to break another bond. Because look, the starting material is the molecular ion. So the reason it breaks to leave a benzyl behind is because it's more stable that way. We can resonance stabilize that positive charge on the ring if we leave a carbon behind in the benzyl group. And the propyl radical goes away. So that benzyl cation at position 91, do they give us? Yeah, they do. So that's why I forgot the term now, reference peak, not the reference peak. Shoot. Base peak, excuse me. The base peak is going to be the one that forms the most stable fragmentation product. All right, so 134 is the whole thing with its cation. Now the cation here on that carbon is probably due to the fact that we've sacrificed one of those pi bonds. So if you hit it with enough energy, you can bust up the aromatic stability. All right. How about, oh, are we saying that, yeah, we can get rearrangement of that far right benzyl cation where the positive charge is on the benzyl carbon. And it says that rearrangement will give us instead a 7-member ring. Does that stabilize it? Probably. That's probably why it did that. So that occurs at 91. All right. So that stability is probably also a reason for the base peak being composed of that particular ion. That's what it says to me. Okay. How about heteroatoms? Alkyl halides, amines, ethers, alcohols. They can play a major role in fragmentation pathways. One of the most important features of heteroatoms is that they often have non-bonding lone pair electrons. These are usually the least tightly bound electrons in the molecule. All right. So when they get struck, that's where you're going to get your positive charge. In the ionization of a molecule containing a heteroatom, a lone pair electron is generally the most likely electron lost to produce the molecular species. All right, that makes sense to me. So here we've got one with chlorine on it. And the molecular is going to be oh, I see what happens. We form the molecular cation on the chlorine, and then we get a transfer of electrons from the bond, from the carbon chlorine bond to the chlorine. It leaves, and now we've got the positive charge deposited on a tertiary carbon. That makes it more stable. And that one occurs at 71. So that one's going to be the base peak, because it is the most stable ion of all the fragments. And we don't get an M plus peak is not there, because we produced a stable fragment from it. It's more stable than the base peak. Yeah. Okay. Here's what they're saying. Since the electrons are being knocked off of the chlorine preferentially, it sets that sequence, it sets that heterolysis in motion. And that means the molecular peak should still have the chlorine on it. But since it became the cation first, and it underwent heterolysis, now we don't have a base peak. We don't have a molecular peak. Yeah. Oh, well, that kind of messes things up, because now you can't calculate the carbons, number of carbons, because we don't have a molecular peak, and it's N plus 1. All right. So what's an alpha cleavage? The elimination of an alkyl group from the carbon atom bonded to the hetero atom. Oh, so this is another fragmentation pattern, right? So if we go through this fragmentation where, yeah, alpha, okay. The alpha carbon is the one attached to the hetero atom. Right? So that tertiary carbon there, right? Tertiary carbon right here, right there. That's the alpha carbon. Alpha cleavage can occur on either side of that carbon. It can occur on the ethyl side, or it can occur on the methyl side. And the two examples there. And in each case, that gives us a chloride with a positive charge double bonded to a carbon. And each one of those, let's see, one is a 106. See, start off 91 and 77. So if we go back, do we have a 91 and 70? Yes, we have a 91. We have a 77. And then the other one, where we lose the chlorine altogether, is a 71. That's the base peak. So that's explaining why we get the 71, 77, and 90, 91 mass charge ratios. It's from those three reactions. Right? The heterolysis, losing the chloride, or the alpha cleavage in two different locations give us these others. Alpha cleavage in amines gives us an iminium ion. And that's very stable compared to the M plus. We still get an M plus here, it looks like. Yeah, we still get an M plus. But it's not as abundant as the iminium, which is the 86 versus the 101. Cleavage in ethers. Where does the cleavage occur in ether? Probably between one of those carbons and the oxygen. So we have very, very small M plus at 102. Fragment ion from alpha cleavage. Okay, so alpha cleavage would actually be one of these methyl groups on the carbon on either side. Take your pick. They're all equivalent. So I was mistaken. It doesn't cleave between the carbon and the oxygen. It cleaves between the carbon and carbon on an alpha carbon. Alcohols, where do we get cleavage on alcohols? Alpha cleavage, okay. In this case, it would be between the number 1 and number 2 carbon. That's the only place you can alpha cleave that one. Oh, we got a fly in the ointment. We've got water. We've added a hydrogen somehow to the molecule and made it's like tacking on a hydronium ion to the molecule, and that gives us 70. All right, other cleavage in alcohols. Let's see if these make any sense. Okay, we can chop off a hydrogen once we form the positive ion. We can chop off a hydrogen, and that gives us a what is that called? It's not a carbonyl. I don't know. Look it up. Or we can chop off another hydrogen from a gamma carbon. Now, why do we have to go all the way over there? Oh, we're losing a hydroxyl in that case, right? The first example, we're losing hydrogen. Second example, we're actually losing a water molecule. So hydrogen coming from one carbon, and the hydroxyl is coming from another carbon, and that gives us water. Carbonyl containing compounds, where do we cleave there? The molecular ion of carbonyl containing compound is typically produced by the loss of a lone pair non-bonding electron from the carbonyl oxygen. Okay. All right. So the carbonyl oxygen in a stable form has 2 lone pairs. We're just going to knock off one of those electrons and give it a positive charge. And then we can have an alpha cleavage there, right? Between, yeah. And that would be an acylium ion. Now say that 3 times fast. But that's going to be the detected ion, right? Not the butyl radical. All right. So this one's got mass 43. So where's 40? There's 43. That's your base peak. So it must be the most common. That's another thing. If you put a known molecule into your device and you look at the spectra and you look at the masses, and then you go back to the original molecule, you can deduce usually which one is responsible for that base peak. It's the most abundant one, so it's going to be the most stable. And we look at this one. So you could chop it in different places and say, all right, what's the spread? What's the mass of this one and this one and this one? And you work your way down and you find out the mass. This is the only one that's 43. So I think that's how they got to this mechanism, by first looking at a known molecule and its mass spectrum, and then working their way back. McLafferty rearrangement. What is that? It looks like we've got a ketone, a carbonyl containing compound, so it doesn't have to be a ketone, undergoes a cyclic movement of 6 electrons to produce an enol radical cation and an alkene. All right, I'll take your word for it. Just memorize it. And then this is the outcome. So what I'm seeing is the base peak is the tallest one. So it represents the most stable ion, I think, because it's the most abundant. So this McLafferty rearrangement gives us a mass of 60. So where would 60 come from? Well, it looks like this group right here is the closest. That's 58. 58. I don't see if that's a 59. So this must be the McLafferty rearrangement. It can occur on anywhere you have a carbonyl group. Ketones, aldehydes, carboxylic acids, esters, amides. Right? Remember an amide? That's an amide. Oops. Okay, that's the last slide, isn't it?